Welcome back, everyone. This is the last final talk of the day. Again, Richard will be giving this talk, so over to Richard.
Okay, so I'll pick up from where I left off, obviously. And so we got down to here. Specifications for control systems is the last thing I did, so I'll pick up there. And I drew a little line. I don't think I'll get to that last topic, but I'll say now, and maybe I'll remember again at the end, that to some extent the lecture that I give on Tuesday will use a lot of the things that are down at that bottom end. So to some extent, if you come on Tuesday, you'll see the things that I don't get to if I don't get there. Okay, so we have these sort of design patterns, and I now want to go in and say, yeah. So I've been talking about what the pattern is, but I haven't said how do you design this, right? The actual control design part. And so I want to do just a little bit on the design of the feedback controller and then the feed-forward controller, right? The two pieces, and talk about, not in great detail, but just, what are those things? What's the computation going on in a kind of traditional setting? And then again, if I have time, I'll talk about it in a more discrete kind of computer science type setting. Okay, so 99%, 95%, let's say, of all control systems actually use something called PID control, proportional integral derivative control. And so I want to tell you what it is. And the kind of important part of it, in some sense, is the integral part. So here we're in this reactive design pattern, and I've simplified it down a little bit. I've gotten rid of the reference shaping bit, right? So I'm just looking, I've got a reference, I've got an output y, I'm comparing the reference to the output, I'm subtracting them, getting an error, right? The speed of the car, whatever it is. And then I have some control computation that is going to command some input. There's some disturbances that are going to get added on, and then I put it through whatever my process is. And probably the most classical type of controller, and it works extremely well, so that's why it's the most used, is something called a three-term controller or a proportional integral derivative controller. This was developed by Minorsky in the steering of ships in the, I think, early 1900s or something like that, so it kind of goes back quite a ways. And it just works extremely well. And the idea is very simple. Suppose that the computation that we do for our controller is given by this formula. I'm going to take the error that I have, that's the difference between my reference, which is what I'd like to be doing, temperature in the room, speed of the car, number of servers that are online, whatever it is. I'm going to take that error, I'm going to multiply it by some constant k. The bigger the error, the more input that I'm going to apply, right? Simple enough. But I'm going to add two other terms. So one term is the integral of the error. And the idea in the integral of the error is I say, look, suppose that I apply that input and I'm still not going fast enough, right? Or the room is still too hot, right? It was 10 degrees too hot in here, so I turned the air conditioning on a little bit. It's now 3 degrees too hot, and it's just stuck there, right? Because the amount of extra cooling I'm applying with that 3-degree error is just not cutting it. Well, one thing you might say as well, if it stays there for a while, right, that error, then push harder. Right? And that's exactly what this term does. I'm going to integrate the error. Right? So if this is positive for some period of time, I'm going to get bigger and bigger and bigger and bigger, and I'm going to apply more and more and more input. So that's the integral term. And then this derivative term sort of does the opposite, which is it says, once you see that you're starting to change, you might want to back off a little bit early. Right? Because I'm now starting to make a difference. If I've got a system that's going to take a while, right? I don't want to keep applying that input, right? I finally started to speed up or cool the room down or whatever, so start to back off a little bit. So this three-term controller, then, you can think of it as having a part that looks at the present, that's this proportional term, the present error. A part that looks at the past, that's the integral of the error over all of the past. And a part that approximates what's happening in the future, that is, what's the rate of change of that input, and I'll use that rate of change to also try and tune what I do. So that term, so I've got a present bit, so feedback is proportional to the error, a past bit, it's proportional to the integral of the error, and a future bit. Now, turns out, actually 95% are PID controllers, probably 94% are PI controllers, that is just these two terms. Okay? So this term often doesn't get used. And so I want to talk just a little bit in words about this term and why it's so important. So what the integral term does is it allows you to adapt to certain uncertainties. In particular, it allows you to adapt to constant disturbances. So suppose that I'm traveling along in my cruise controller, and I go up a hill, right? And I slow down a certain amount, and then I press the gas, right, to speed up, but I don't speed up enough, right? Then you're going to have an error still, so you're going to press harder, right? And you're going to still have a little bit of error, so you're going to press harder. When are you going to stop pressing? Well, when the error goes to 0, you're going to stop changing it, right? So in other words, I'm going to integrate this past error, and at some point this integral is going to have some value, and that value is essentially the amount of additional input I needed to apply to compensate for that hill, right? And so without even knowing like the steepness of the hill or anything else, I essentially figured out, right, how much extra input do I have to apply to completely exactly cancel that. And if you design this right, if the system is stable, that is the error goes to 0, right, then the only way this system can be stable is if the error essentially goes to 0, right? Otherwise this thing's going to constantly keep integrating up or down depending on whether it's positive or negative, right? So whenever you put integral feedback in, what you're sort of guaranteed if you design it right is that the error will go exactly to 0. This is what your car uses, right, to go to exactly 55 miles an hour. You go up a small hill, right, it'll push a little bit, right? You go up a bigger hill, right, it'll integrate up and it'll push more, right? And it will get it up to the limits of the amount of input you can apply, right? Obviously, if I go up a hill that's so steep that my engine cannot apply enough torque in order to go up to it, right, something's not going to work anymore and I'm going to have to slow down. Yeah.
We're not worried about numerical aspects.
They haven't been a big issue, right? So, meaning people have figured out how to do these numerically correctly and get rid of the noise and other things. So, yeah, I'd say it's a practically solved problem. So, okay, so these PID controllers turn out to be, sort of ubiquitous because they do lots of things very well. They're in all of the heating systems. They're probably in your battery power supplies and lots of other places that that are sitting there. And they're a way to allow the system to take into account constant disturbances, or maybe your car is heavier than it normally is. You'll compensate for that too, right? It's all sorts of uncertainty, right, that gets kind of compensated for, right, with an integral term. Now the derivative term, just to say a little bit about it, is typically there for systems that have long delays, right? That is that I've applied some input, it's starting to turn the right way, and I still have an error potentially, right? And so I'm still going to apply at the least this proportional term, but now until this error goes through 0, I'm going to still apply, right, the same sign of the input. And sometimes you say I need to back off more quickly than that, right? So that derivative term is an anticipatory term that says I'm going in the right direction. You use it for systems where you need to anticipate ahead of time. It came up in ships because ships are very slow, right? And so once you're trying to turn and point to something, right? And if you don't start backing off on how hard you're turning, you'll overshoot. Right? And so it's a way to kind of keep it from overshooting. So that's why Minorski, right, came up with this 3-term controller. Okay, so how do you design these things? Well, essentially we need to choose the gains. There's 3 numbers in here, right? So I give you a system. I've got some model of that system. I've got to do some analysis on that model. You can, sort of dumb way to do it, but you can think of it as I'm just going to simulate the system a whole bunch of times, right? Pick different gains and find ones that do the right things. What do we want it to do? To this question that came up earlier, what's the specification? Well, first, we want it to be stable, right? That is that we want that when we put this feedback controller in there, that we converge to a fixed speed, right? And not oscillate, right? Because we could oscillate with this stuff, right? I could integrate the error and I apply a bunch of input and then I start to slow down and then I integrate the other way. You can get oscillations quite quickly out of this if you're not careful. I want performance, so I, for example, want to track the reference. And again, I would say something like I want, within 5 seconds to be within 10% of the desired value, and within 20 seconds to be within 0.1% or something like that. I probably also want that the disturbances should be attenuated. Remember in my cruise control example, this was the hill, right? And I want the effect of the hill, right? If I didn't have this controller in there, I would just hold the gas at some level, and then when I went up the hill, I'd slow down. Right? And so I've got some effect. I'd like less effect than that, right? Instead of slowing down 10 miles an hour when I go up the hill, I slow down 0.1 miles an hour or something like that. So we can write those things down. And finally, we want it to be robust, right? So there's uncertainty in this. I may not have an exact model. My controller gains may not, depending on how I implement them, they may not be exactly right. Like if this was an analog circuit and they were implemented with op amps and resistors and capacitors, they might change a little bit over time, right? All of those things. So I'd like that these properties are true in the face of disturbances, so no matter what the disturbances are, or what shape they are, what types of frequencies they are, but also, and again, I've left it off, but implicitly you should think about, I know this is only a model, I know that it's not exactly right, and I'd like it to still work even when that model is approximate. And so we know how to prove things about that. So a PID controller, and there are lots of tools that allow you to do this. Roughly speaking, you would sort of give it a process description, and then you would maybe play with these gains by hand, but there are also things that you can do automatically. You kind of press a button, and it goes and it moves the system around a little bit, and then it says, here are the gains to use to stabilize that system. Right? So these are called auto-tuning systems, and they'll do that automatically. And most, like process control, if you want to control the temperature of a reactor or something like that, they'll use PID controllers with auto-tuning, and they'll figure out what the gains are, so that you put it on a different reactor of a different size with different types of materials in it, and the controller just automatically figures out how to control it to the right temperature. So that's kind of standard technology these days. All right, another type of control design is in this second design pattern, where we might have something that looks like a feedback design. And so let's imagine we have a process, and let's suppose, for example, that's written down as a linear set of differential equations. So here x is a vector of states for your system. Maybe it's an airplane, and it's the position and velocities and attitudes and angular velocities, for example. And I'm going to assume it's linear dynamics, which an airplane wouldn't be, but would be around an equilibrium point, right? If I do small perturbations, I could kind of linearize the dynamics. I've got some input that's going to apply, and then I have some output that I measure. And here what we're going to assume is that although I care about what the output is, that might be like the speed of the aircraft or its position or something like that, I'm going to assume that I measure the entire state. Now in reality, I probably measure this output. Remember I had that observer, right? And so I'll have to observe the entire state. And it turns out there's a very nice separation principle. You can show that if I design as if I was measuring the state, right, and then I observe as if I knew what the control input was, right, I can put these two together, compose them, and it will work. All right? And so we'll often do the design assuming we can measure the full state, and then we'll do the observer design assuming I know what the controller is, right, and then the two of them fit together. Okay, so the pattern here then is I have my reference input that comes in, I have my state that comes back. This reference input is now giving me some desired state. So this KR is like a vector that says for this reference input, here's what your desired state should be. It's a very simplified version. It only works because the system is linear. It's going to turn out that indeed, as a function of what the reference input is, the amount of input that you should, the desired state is going to be a linear combination or linear function of that reference. And then I'm going to subtract essentially kx from this. So that's what it sort of looks like as a block diagram. Now, if it's a linear system, I can actually write down the solutions explicitly. It's a convolution equation. I can write exactly what this system does, so I can plug everything in and sort of solve things out. And if you do that, if I apply this control law, then it turns out that the dynamics have this form. And essentially what's happening, it's not too hard to see, if I put in here u is equal to r times kr minus kx, right, so this particular controller, then I can just plug that in and I get this guy. And now, if I, just for simplicity, assume, for example, that this reference is 0, then you can see I have a linear system with a minus bk times x. This is we call it the dynamics matrix, or the system matrix. It's just a linear differential equation. And we know that the stability of a linear differential equation is determined by the eigenvalues, right, of that matrix. And so I can move the eigenvalues by applying feedback. I have the natural eigenvalues of the system that came with the A matrix. But if I look at A minus BK, right, I can change those eigenvalues somehow, right, through doing that. Okay, so the idea here is that we get this system that kind of in simple form looks like A minus BKX. Stability of the closed loop system is just asking that we find a K that makes this stable. So you can think of this like a matrix pencil or something, right? There's a certain set of directions that I can go, and I can get eigenvalues for those different directions, right? An interesting question you can ask is, where can I put the eigenvalues, right? Whereas I give you an A matrix that has some natural eigenvalues. I give you some inputs. I can apply state feedback. I can now go to all of the eigenvalues of this matrix where K can be any set of gains that I want to use. I'm going to multiply the state, right, times that K matrix and use that for the input. So we can link those eigenvalues to performance, but we can also ask, where can we place them? And the answer is, we can place them anywhere under certain conditions on the system dynamics. So turns out there's a test that you can do called the Reachability Test. And if this system is reachable, and most systems are reachable, then in fact I can put the eigenvalues any place I want. That means I can design the dynamics of the system, right? Because the dynamics of the system are given by the eigenvalues, right? That determines the response of the system. The time response of the system is determined by the eigenvalues. So indeed, if a system is reachable, and we know how to both check if a system is reachable and design it to be reachable, you can do that. It might seem a little bit odd because, for example, I might have 12 states and only one input. But remember that I'm kind of getting to apply that input vector over time, right? And at different states, I get different inputs that I apply. And it just turns out that you can set arbitrarily the eigenvalues of this matrix, right? Even if this is an n by n matrix and this is an n by 1 vector, right? Turns out you can show that you can, under certain conditions of reachability, set that. And again, those conditions are usually satisfied. So how do we actually design this? For a simple system like this, we essentially, the design problem is to say, given A and B, find K such that the eigenvalues are at specified locations. So that's a MATLAB command. Right? That's called the place command. All right? So you give it A, you give it B, you give it desired eigenvalue locations, it gives you the matrix K. Done. Right? So that's control design. So you can do fancier things. You can say, well, you know, maybe I didn't want to place the eigenvalues in given spots. Maybe I wanted to minimize some cost function, like minimize the integral of the error plus the integral of the input, right? So I want to keep the error small, but I want to trade that off with the size of the input that I have to apply, right? So if I did a quadratic cost on the error and I did a quadratic cost on the inputs, all right, then I could have a positive definite matrix Q that told me the error weighting, and a positive matrix R that told me the input weighting. And if you call the LQR command, linear quadratic regulator, it will give you the gain K that minimizes that integral. Done. Okay. So if I can convert my problem into this form, right, I just have to call a function in MATLAB or Python and I will get the gains. And this is what we do. Right? So it's like, you know, you give me a room, right? And I say, okay, well, here's the dynamics of this room. I now have, you know, to figure out what the state, what the temperatures, et cetera, and I gotta figure out how much to turn the heating on, right? So I give you A, I give you B, I give you some cost functions to say how much does power cost, how much are you willing to tolerate the differences in temperature, right? That's the Q and the R matrix. Give me the optimal controller that minimizes that quadratic cost. Why quadratic cost? Because that's the problem we can solve, right? You know, is that the right one? I don't know. You probably, you know, like does it really matter whether it's 5 degrees or 10 degrees, right? You know, maybe you want some, you know, okay, can't solve that problem anymore, right? So we can solve this problem, right? So this is the problem we solve. All right, so that's sort of what happens. And again, I'll just point out that essentially we're designing the dynamics by choice of feedback, right? I mean, this is exactly, right? You know, I want to design it to minimize this cost function. I want to design it to have these closed loop eigenvalues. You know, give me the feedback controller that does that. Okay, so for feedback, those are the two primary techniques that we use to start with. PID control, with the integral being very important, or state feedback, often using linear quadratic regulator theory, sometimes using pole placement, what is called pole placement or eigenvalue placement. As I mentioned, the student came to me, you know, that's only part of the problem, and increasingly that's the simple part of the problem that you got to do right, but it's not the part that gives you really good performance. The part that gives you really good performance is the feed forward part, the planning part, right, that sort of front end. So how do we solve that problem? And so let's talk a little bit, oh, sorry. Yeah, sorry, I said I would stop and I didn't. Okay, so let me stop on the feedback. I did PID and I did state space.
So what are some desirable eigenvalue configurations? Like what I mean, of course you want stability, so I guess you want the negative.
Left half plane, right, or if it's discrete time inside the unit circle, right?
Right. But anything more? I mean, is there anything more?
Yeah, so typically, you know, what'll happen is that you would say, well, I want my system to respond fast. So the speed of response is determined by the eigenvalues. So you might want to put your eigenvalues out pretty far to the left, right? Because if you have any eigenvalues that are very close, right, you're going to get in the solution of a linear differential equation, you're going to get terms that are e to the lambda times t, where lambda is that eigenvalue. If that has negative real part, so it's stable, but small negative, it means the rate of convergence to 0 could be very slow. So you'll put them out. So why not put them way out to the left? Well, you can do that, but you'll get very large gains, right? Because now, right, when you want to move those eigenvalues very far away, the K matrix is going to be very large. What does that mean? It means if I have a very small error between the actual state and the desired state, I'm going to apply a huge input, right? That might be okay, but if I had noise, for example, in my state estimate, that gets amplified too. right? So there's a fundamental trade-off that we understand, which is that you need to, and it's the reason that people don't do eigenvalue placement so often, because that trade-off is hidden, right? It's in there. I can pick the eigenvalues and then tell you how bad it was, and they say, oh, that's not very good, let me pick a new one. The linear quadratic regulator lets me specify that explicitly. I can tell you what's the trade-off between error and input that you want. And the linear quadratic Gaussian problem, LQG, allows me to also estimate the effects of noise and disturbances in a stochastic setting, and so we can put that in there as well. But other questions on PID or state feedback? Yeah.
If I have such a sort of complete description of the process behavior already anyway, can't I easily do the planning anyway, or trajectory planning?
You could, assuming that there's no uncertainty.
Okay.
Right, so again, right, you put in the feedback in there to compensate for the uncertainty. The eigenvalues, if I have some uncertain dynamics, so that A matrix isn't quite the A matrix, right? In fact, I could have an A matrix that went between stable and unstable, but A minus BK might always be stable, for example, right? Yeah, good question. Okay, so now let's talk about the feed-forward part of this problem. Okay, so now I want to talk about that trajectory generation block. And again, remember that the setup for this was that I've got some reference that's describing my task that I want to do, and I now want to compute out a set of states and an input that achieve that task. And so a way to think about that is that I'd like to find an input u such that I minimize some cost function, so say some integral cost function over some finite period t, subject to the input and the states satisfying the dynamics of my system. So I want to find an actual solution to my dynamical system. So this is the model for this process P, right, is x dot equals f of xu. And I also may have some constraints on the states or the inputs. My input can only get so big, right, for example. And so the problem that we want to solve is, perhaps, I mean it's a standard one, minimize some metric, right? And a typical one would be the integral over time or integral over space, right? If you want to do something spatial, you could do that as well. And we'll usually put in that we want to do it over a finite time. Sometimes you can do infinite time, but often finite time, and then we'll put a terminal cost. So like, I want to get, you know, close to the Oakland airport, but just plan out for the next 5 miles. Right? And then, you know, at the end of that, be closer, you know, it's better if I'm closer than if I'm far away, right? So, and I'll just lump all of that into this terminal cost B. And so that is just a constrained optimization problem, like the ones we saw all yesterday, right? I mean, just solving, right, you know, sort of constrained optimization problems. And so we can do those sorts of constrained optimization problems. And the trick is that we need to do this, at least as I've shown it here, I'm just doing it every time the reference changes, right? So the reference changes, you say you want to go faster, compute out a new trajectory. You want to go slower, compute out a new trajectory. Remember that eventually I'm going to do this over and over and over again. I haven't gotten there yet, but we do want to do it fast. And so there are a lot of tricks to get very fast solutions. And so I won't go through all of those, but just to say that, and I showed you what 15 years ago we were computing these things out actually at 100 hertz. So we would calculate out what to do for the next 10 seconds, every 100th of a second, right, on something with about 9 degrees of freedom and a, you know, relative, and it, you know, costs us $30,000 at the time. Do it on your iPhone today, right? So again, the reason these techniques are working is because computing, right, Moore's law, all of that stuff is just getting to where we can solve these things. You can encode the whole thing in, you know, various types of neural networks and other things if you want to. As I already mentioned, we need to update the solutions at the rate at which the reference is modified in this kind of a scheme. And the other thing is that we can take into account over here a couple of things that are harder to take into account over here. So the feedback control designs that I showed you, for say the state space one, I gave you a linear model. But if you have global nonlinearities, input saturation, state space constraints, actually what you want to do is take those into account on the trajectory generation side of the world. And then what I'm really trying to do is I'm trying to regulate the state of the system to be near XD. And if that's small, that is I had a pretty good model of the system and the disturbances don't take me too far away from where I expect to be, then I can linearize the dynamics, right, around XD, and I won't get very far away from it. It's like if the controller's doing a good job, it'll keep you near the thing that allows you to make the assumption that you used a linear model, right? It's one of these circular arguments, right? I'm going to use a linear model to design a controller. If that controller's a good controller, it will keep me near the place where the linear model is valid that I used to assume I could design the controller in the first place. And that works, okay? So that's what everybody does. So if you go look at an aircraft flight controller, this is what it's doing. It's generating the trajectory to come down and land like the auto land system, and then it's regulating around that. Right? It's got to stay in the center of the runway, got to come down at the right flight angle, all of that stuff, and it's doing these sorts of calculations on the inside. And so, for example, you might say, well, this ducted fan that I showed you, the little flight control experiment, you might want to go from this position to this position. That's a person standing there, let's say. This is the roof, right? So I need to get from here to here, right? So I need to go from point A to point B in t seconds, right? While staying away from these obstacles or something like that. That would be the typical problem that you solve. And again, I have to use a model here, right? Because I've got a model of the dynamics. That model may not be right. But that's okay, because I'm going to put feedback in here as well to compensate for that, right? So if the model's not quite right, then this input won't quite do the right thing, right? It wasn't quite the right dynamics in my calculation. I'll be off by a little bit. When I'm off by a little bit, I'll see that I'm off by a little bit. I'll correct for that, right? And so it all kind of works. Okay, so this use of the feedback, we often call this the inner loop, right? Because there's an inner loop, is used to track it. And that corrects for disturbances and model uncertainty. So the way we normally think about it is that you use the trajectory generation to handle these sorts of things, global nonlinears, input saturation, state space constraints, that are hard to deal with here. And then you do what you can here, which is to deal with the disturbances and the dynamics and the unmodeled dynamics. And this is often called 2-degree of freedom design, because you have a kind of design degree of freedom here. What cost functions do you use and other things, as well as a design degree of freedom here. The cost function you use for this may not be the same as the cost function you use for this. Depends. You can decide they're the same, or you can decide they're different. Now, the other thing, as I've already alluded to, that's quite nice is, as I've sort of done it here, I get a reference, I can do a computation, and then it's all feedback. But in fact, what we do in practice is we take the same kind of design pattern and we wrap this outer loop around it. And this outer loop looks at where did we actually get, and then we recompute the trajectory from where we actually got. And so the computation that we typically implement looks something like this. I'm going to calculate out that same integral over the time period t from now to capital T, and then I'm going to apply the input for time delta t. So think of capital T as 10 seconds, and think of delta t as 1/10 of a second. Right? So I'm going to calculate, here's what to do for the next 10 seconds. Do that for 1/10 of a second, then recompute to what to do for the next 10 seconds. So this is called receding horizon control, because I keep receding on the horizon. Or sometimes model predictive control, because I use my model to predict what to do. So you'll hear these terms used interchangeably. Model predictive control or receding horizon control. And kind of the way it looks is something like this. So if I forget the feedback controller for a second, we're not going to really do it this way, but pretend. And then the calculation might look something like this. So you're looking at the state, a one-dimensional state for simplicity. You're looking at time here. And what I'm going to do is I say I know I'm at this state right now, and I'm going to compute out for the next capital T seconds this curve, right? This red curve. So this is the calculation that minimizes this cost function from this initial state. And then what I'm going to do is I'm going to apply this input, the input that corresponds to this state, I'm going to apply for the first delta T seconds. Now, of course, the model might be wrong. There are disturbances that I didn't take into account, right? There's no disturbances in here because I don't know what the disturbances are, right? So I might not actually end up where I thought. Maybe I end up here instead. So I have some error. What am I going to do? Well, I know where I'm at, so recalculate from there. So now I recalculate this next trajectory out for capital T seconds, starting from where I'm at. And then I apply it for delta T seconds, and then I see where I end up, and then I keep doing this, right? So the curve you actually follow, right, might be this blue curve, right, as I do this. And it's, again, it's a feedback mechanism, right? I'm just calculating out, right, how do I do this? So that idea is called receding horizon control. It's another way of doing a feedback loop around the inner loop. Here I've sort of described it as if we don't use this at all. We usually do. That is, we use both loops, but you don't have to, depending on things. Now, one thing I'll say about this is that you do have to be careful about the terminal constraints. And the reason is because you're minimizing over some fixed horizon, and you have to be careful that your optimization over that, let's call it short-term horizon, takes into account what happens after that somehow. Because I could make the right short-term decision but ignore, right, sort of the implications longer on. So if I don't put any terminal cost here, it's like I don't care what happens after that, just minimize over the next 10 seconds. And if that means that 10.2 seconds from now you're right in front of a wall, right, I'll worry about that later, right, like 0.2 seconds from now, right, or 10.2 seconds from now, right. So that's not a good idea, right. So you want to do something that says, look, by the way, you should end up at a reasonable state as well. So there are mathematical conditions on what this has to satisfy in order to make sure that this whole thing is stable and works correctly and converges and does all the right stuff. And that's a very well understood theory. And as I already said, so 95% is PID, 4.99% is this, right, what's left, right? And all the fancy stuff is this. So I showed you this video already, but I'll just replay it. This is receding horizon control running. It's actually not even running the inner loop. We can calculate so fast that we don't even need the inner loop. So we're just calculating out for the next 10 seconds what to do. We do that every 100th of a second. We apply it for 0.1 seconds. We recalculate. There's constraints. There's actually a guy sitting down here. And so we're missing him every time, right? There's constraints on the top and the bottom. There are actuator constraints, right? All of this stuff works great, right? And so, very robust, right? Very high performance, right? For this type of system. This is what, fighter aircraft use and all sorts of very high-end systems. But it's also what this system uses. Because we're calculating out for the next 10 to 50 meters, depending on how fast we're going, what to do, and recalculating, and then implementing. Now there's other higher level stuff going on, but the trajectory generation part of this is saying, well, go down the road for as far as you can see, and here's the trajectory to follow. But every time I see a little bit more road, I calculate out what to do next. And if I don't quite follow the road, I also take that into account, right? So I'm just constantly recalculating this thing, again, at about 100 hertz for this particular system. Actually, it's between 10 and 100 hertz, depending on how complicated the obstacle set is and how long it takes the optimization to perform and other things. So that's what's being done, and this is what more or less every autonomous car is doing, right, is some version of this, right? You might do the trajectory calculation on a graph, you might do it with some sort of convex optimization, everybody's got their own tricks, but you're just redoing that calculation over and over again and doing receding horizon control. Okay, so that is sort of the trajectory generation. First you want to just generate those trajectories, but really it's become, the pattern has been to wrap this receding horizon control loop around everything at this point for most of the things that we look at. And I should say, I guess, when you do, sometimes they don't. So if you're doing scheduling, for example, suppose you've got a bunch of chillers up on the roof of this building, right? And you might say, well, I'm going to schedule when those chillers are going to turn on, but then I'm going to modulate the load on the chillers. That is, which chillers turn on, how many I turn on. I might do that once a day. All right, so I just say, hey, it's a Wednesday, it's going to rain, so I'm going to just calculate out, I'm going to turn that chiller on at 2 o'clock, and then I'll turn this other one on at 4 o'clock. Sometimes that's a open loop once a day calculation, right? Because it might be easier to do, or your software doesn't handle it, or you don't want to start and turn on and off chillers and things like that. Okay. Questions on the kind of feed-forward part of all of this. As I said, a lot of the performance you see in modern systems is because they're making use of more computation and doing these feed-forward calculations. Okay, so last topic then is I want to talk a little bit about layering and sort of how all of this stuff comes together. And so I'm going to do that by sort of talking about how we do a control design on a typical system, and then some of the tweaks on that or additional challenges. All right, so I've got some physical system that I want to control. Pick your favorite application. This might be the heater in this room, it might be your car, it might be all of the routers on the internet, it might be the planet, if you want to do geoengineering, right? You pick, right? Your Segway, right? Anything that is some physical process that's got feedback around it, which is pretty much it. Now, I've got some external environment that interacts with. This is the source of my disturbances, right? Remember, there's unmodeled dynamics. Sometimes we sort of think of that as the external environment, right? And we kind of lump it there. But I've got that there. Now, the very first thing that we typically do when we're doing the design is we build a model of both the system and the environment. And we use that model to redesign the system. I've got to decide how big a chiller do I put on top of this building. I've got to decide that before I actually start controlling the chiller, right? So I've got to make some estimates of what the loads on the building are going to be and how big a classroom do I have and what's the heat capacity and all that stuff. It's a car, how fast do I need to turn the steering wheel? If it's an airplane, how big a control actuators do I need? So you do all of that, and you might iterate on the design, right? You might go through and say, well, you know what? I actually need to reiterate my design and put faster actuators, different configurations, right? So you do the standard sort of a thing. And then once you've got a design you like, then you might say, okay, good. So now I want to make sure that at my lowest level, I can get good control properties. I can follow that trajectory, right, given a trajectory. And so we would do the lowest level controller, where we would say, well, I've got to decide what sensors I'm going to put on. Here's my observer, probably a Kalman filter at this stage. I've got some actuators that I need to put in there. And I've got some sort of a feedback controller, probably a PID loop at this inner level. And as I do this, right, I might find out that I need to redesign this. Actually, you know, when I go and I look at the response time, it turns out that although I can hold the temperature at a good level, it takes me 3 hours to get the temperature in this lecture hall to the right temperature when a bunch of people walk in. That's too slow. So I'm going to go redesign it. I didn't see that until I actually went and maybe, you know, tried to design the control loop and with the sensors I've got and other things, right? So you might do more design iterations, right? So you might iterate on this, update the model, update the system design, update the controller, right? Go through that. Then finally you get to the point where you say, okay, good. I think I can hold the temperature in this room. I think I can hold the velocity of the car. I think I can maintain, you know, whatever variables that I want to maintain in some system I'm controlling. And then you might go up to the next layer of the design. Say, okay, good. So now I want to start moving this thing around, right? I want to ramp up the temperature in the morning and get it to the right temperature. And so now I'm going to do online optimization. That's the feed-forward part of this loop. And I might do more complicated things on the state estimation side as well. For example, I might like a deep neural network that predicts what the loading on the building is going to be based on past patterns, right? So that I know that ahead of time, right? Because it's kind of hard to figure out, right? You go exactly how many people are going to be in the lecture hall, you know, how many different programs are going on, what day of the week is it, right? All that stuff. So you might use moving horizon estimation. That's kind of the opposite of receding horizon control. Look back over time and estimate where things are. You might use deep neural networks and classifiers and other things. You pick. But this is a higher level of reasoning going on. And then, of course, I might do, you know, additional design iterations, right? Oh, you know, in fact, right, I need to change something. And then finally, usually multiple layers, but you get up to the kind of discrete decision-making layer where you have to make discrete decisions. Those discrete decisions could be about discrete choices you make. When do I turn certain things on or off? They could be about mode and contingency management. What am I going to do if I get a flat tire while I'm landing? Right? That's a discrete thing that occurred. All of a sudden, my landing gear don't go down, right, or something like that. If it's a plane with a pilot, you're going to, I guess, land in the Hudson or something like that, right? If it's an autonomous plane, the autonomous plane has to decide what to do. So we have these kind of layers of abstraction that are somewhat natural across, you know, many of the types of systems we design. Now, the environment, you know, I sort of drew it as affecting things down here. Here's the noise coming up. Here's the disturbances. I might, you know, have a feedback interaction with the environment. In reality, of course, the environment, and that didn't come out very well, so it should be shaded there. So the environment, in fact, affects all of the layers of the design. Right? So you have some representation of that. Now, the other thing that happens these days is we have a lot of networking communications that connect all of these things together. And that also kind of feeds all the way across this system. Right? So all of this is part of a big network system. And what that has done is to say, geez, I can have lots of computing available to me. Right? And so maybe, in fact, what I should do is, instead of just having a fixed system model, right, maybe I should have an online system model. And I can recompute all of these things, right, based on my actual model at the time. So I'm in my car and I have a failure of the tire. I got a front tire that's flat. I can say, great, I can recalculate the dynamics out. Now I can resolve my trajectory optimization problem with a left tire that's flat, right? And actually calculate how to do that without having something bad happen. So people are now moving to online models and recomputing. It's like I'm doing the system design every 10th of a second, right? Instead of designing it ahead of time and then implementing it, right? I'm actually just recomputing all the time, right? So it's like I'm doing the system design online. So we might do something like that. The other thing that you tend to find yourself doing is, rather than having one optimization run or one decision-making algorithm run, you end up getting lots of these, right? Because you say, you know, driving in a parking lot is different than driving on a highway, is different than driving in an intersection, so I'll have different things that are running, and sometimes I can't tell, right? I want to have an algorithm running for the case where somebody cuts in front of me, but I want to have another algorithm that's calculating out what to do if that doesn't happen, right? So you start getting lots of things running all at the same time for different patterns of behavior or input or other things. And as soon as you start doing that, then you start having to worry about these things run on distributed computing platforms. So time matters. Right? So now all of these things are on slightly different clocks. Why does that matter? Well, because now you've lost global synchronization. So suppose that what happens is that one of your processors sees something jump in front of you, but another processor, that message hasn't gotten to it yet. Does that matter? What happens if they happen in the other order? How do you make sure, right, that somehow these things behave properly when we've now got this complex event system, right, with different interleavings of events happening all the time? Tricky. Throw on top of that, you know, as soon as people put networking communications in, they say, geez, why do I just have to communicate with the computers inside my car, inside my airplane, inside my building? Why don't I communicate with the outside world? Right? So now you start doing, right, cloud resources, different operators, other subsystems. We start interconnecting all of this stuff together. So this is what a modern control system looks like. And this is what we've got to go design to. Now, it's all just feedback loops and design of dynamics and managing uncertainty, right? But it's complicated. So in some sense, it's still just sensing, actuation, and computation, the old style of control. But in very much, it's really about dynamics, uncertainty, feed forward, and feedback, right? So Duff beer all the way across all of these layers. So the field is exciting right now because we've got these really complicated systems that we have to go implement. And I would say the systems we saw yesterday are examples of that, right? In some sense, we're not necessarily, it's not the only problem to solve the feedback control problem, right? But there's a feedback part of that problem as well. Okay, so lots of examples of systems that look like this. So aerospace systems look like this, self-driving cars look like this, factory automation systems look like this, smart buildings, smart grids, smart transportation systems look like this, right? I mean, these, they have these multiple layers, they have all these things going on at once, they're distributed, right? All of that stuff. Right? And so we have answers for some pieces, other parts we don't. There are lots of interesting challenges. Certainly one is, how do we define the layers of this, right? So we want to break our design apart into layers, right? What is the inner loop? What is the trajectory generation loop? What is the discrete decision-making loop? You'll have discrete variables down at this level, so what the heck's going on, right? I mean, it's just, how do we break apart the problem? Standard computer science problem, right? You want to make a multi-layer hierarchy, where do you put the layers? What are the interfaces between the layers? All of that stuff. And so we think about that, for example, as when I create those layers, I have to have an understanding at this layer of the design, I want to treat the lower layers as just a simplified abstraction. And so I've got to have some contract that says, for example, the online optimization is going to assume that if I tell the lower level feedback control to track this trajectory within 10 centimeters, that it's going to do that. Because now I know that I will stay within 10 centimeters of whatever trajectory you give me, so I can use that for my planning purposes. Right? Because I need to know that you might be up to 10 centimeters off. On the other hand, that lower layer has to say, look, I can't stay within 10 centimeters if you tell me, to turn, really sharply at 20 miles an hour and you want me to go around a really sharp turn. I can't do that. I mean, just physically can't do that. So I have to assume that you're going to give me, right, reasonable trajectories. And under the assumption that you give me reasonable trajectories, I'll guarantee I'll fall in within 10 centimeters. And then the other part has to say, okay, fine, if you guarantee you fall in within 10 centimeters, right, I'll guarantee, so I'll assume you're going to fall in within 10 centimeters, I'll guarantee that I give you reasonable trajectories, right? So you get a set of assumed guaranteed contracts between the layers. We call these vertical contracts. So at every layer of abstraction, you need some vertical contracts about what can I assume about the layer above and the layer below, right? And what can I guarantee to those layers, and then those will turn into assumptions for the other layers, or at least my assumptions should be bigger than the set of guarantees, right? So that one fits within the other. So that's one way to do it. The other is that many of these systems are distributed, and so we have horizontal contracts as well. Right? I've got a whole bunch of bikes out there, a whole bunch of cars out there, right? And they're all interacting with each other also within each layer of abstraction. So if we're doing platooning or something like that, somebody asked about that, right? Then of course, the controllers at that low level are all interacting with each other to try and maintain things. And I better have a set of contracts that say, if you implement these assume guarantee conditions at your layer of abstraction, then when you interconnect with other things in that layer of abstraction, you'll be okay. So we call those horizontal contracts. So we need vertical contracts, we need horizontal contracts. We also, of course, have to remember to think about things like stability, robustness, and a big one for control systems that we typically have not done is security and privacy. Right? So Stuxnet was a SCADA loop, right? So SCADA, supervisory control and data analysis, or whatever SCADA stands for, right? The C, I'm pretty sure, is control, right? And so guess what? I'm going to assume that any command that comes across my bus is valid. Right? Ooh, that's maybe not such a good assumption if somebody put a USB key into a computer someplace, right? So a lot of systems, right, we've not thought about, right, how do we guarantee that these are secure? And especially as they become network interconnected, right, and autonomous cars become network interconnected and they start feeding information, right, we got to start worrying about that. Privacy the same, they can leak information that you don't want to leak. Okay, so these layered approaches to design I think are very interesting, and we're starting to think about them, and they enter in all of these systems. And again, at each layer there are these sorts of control problems. Between layers are these sorts of control problems. I'll just say what I said before in terms of the way we think about these. At the physical layer, you might start with differential equations and constraints on set, and you're thinking about things like how do I optimize the operating envelope or the energy efficiency. At the regulatory layers, you get these funky formulas that the control engineers love, right? That are telling you things about transient and steady state response. At the next layer of abstraction, you're probably solving some sort of an optimization problem. This optimization problem here I've written as a sort of deterministic optimization problem, but it might be on expected values and moments and other things. That's all fine. You can do a stochastic version of all of this. And then at the highest layer, you probably have some sort of a finite state automaton in one of these formulas that the computer scientists can read, but most of the rest of us can't, right? That is describing some sort of other types of properties. So let me just say a little bit about, I'm going to kind of talk a little bit about these two layers, because that's where our current work is. And this is kind of a preview of some stuff that I'll say on Tuesday. All right, so I kind of want to focus on things at these layers and the interactions between these layers, just to give you a sense. So let me first start by defining these funky symbols. And so this is an area called temporal logic. There are lots of different temporal logics out there. The one that we tend to use, because it's kind of the simplest and fairly common, is linear temporal logic. So in linear temporal logic, we want to look at sequences of events. There's no explicit notion of time. There's just events that occur, and they're ordered. And we want to write down formulas about the events that occur. And so we define a couple of operators. The diamond means eventually, and that means something is eventually true if at some point in the future that property will become true. You will be in the correct lane, you will stop, you will turn left, whatever. The box means always. That means that should be true at all times. You will not run into other cars. You will always be at least 1 meter away from other cars. Right? Something like that. You will always use less than the power that you have available. And then there's some other funky operators that we won't use. And so you can think of this as I've got a sequence of, so if A is some proposition, and I've got a sequence of events sort of written as if they were linear in time, I mean at fixed time intervals, but these could occur with any amount of time between them, then whenever an event occurs, if I say eventually A, I could have that A is not true, so not A, not A, not A, but at some point A must be true, and then this operator is true on a sequence if A is true at one point, and after that I don't care. It's just eventually true, once, that's it. Always, of course, means that A should be true at all times and never not be true. And the interesting things come when you start combining these. So for example, I can say always eventually proposition P is true. That's a liveness condition. Right? Always eventually check in your left mirror. Always eventually make sure your bike has 100% of it, or 95% of your bikes are there. Always eventually, right, make sure some other property is true, that the room gets locked up. Right? I can also do it the other way. I can say eventually always. What does that mean? That means that at some point in the future, it will be true forever after that something is true. It is eventually always true that you are within 10 centimeters of the runway line. That might be one that you like, right? Because you like to stay within 10 centimeters of that runway line, right? Not just get there once, right? Go skidding across it, right? I want to get there and stay there, right? So this is like a stability property in some sense. And there are lots of other things that you can do with these, right? So you can say P applies eventually Q. That's like a response. If P happens, then eventually Q must happen. Now, a problem with all of this is that in computer science, these are events that occur, but there's no notion of time. How long does it take? So people have started to extend it with things like metric temporal logic. We use something called signal temporal logic. And in signal temporal logic, you add some set-based things that aren't important, but you also add time bounds to things. So you might say that between time t1 and t2, P should be true. Right? Or P implies that eventually Q has happened between time 0 and t. So within t seconds, I get a response. So these sorts of temporal logics are things that can be very important. And so we can now write down specifications in this language. So let me sort of skip past this stuff. So I won't do a really simple example just because I want to get to some of the other things, but here are some examples of those things. Now, one of the things we can do is think about this now from the point of view of a control system. So suppose, for example, this is my standard, right? Standard model for control. Right? Except now my process dynamics, my environment dynamics, and my controller dynamics, they're going to be discrete state finite transition systems. Right? So finite state transition systems. So I'm going to go from state 1 to state 2 to state 5 to state 6, which might be the number of parts in the queue, or right, do I turn left or right, various things where you have a discrete state. And I might have a specification. And here I've written one, don't worry about what it is. It's sort of not written in a good way. I might have some specification made out of temporal logic. And now I can say, great, I want to call LQR. Right? I've given you a specification, minimize this cost function. I've given you a description of the system, x dot equals ax plus bu. find the controller, right? What would the equivalent be here? I've given you a finite state transition system that describes the dynamics. I've given you a temporal logic specification. Synthesize the reactive controller. If the environment does this, you do this. If the environment does that, you do that. Right? So that would be the equivalent of this. So that's a great problem to go solve. This is a synthesis problem. There's only one problem with that synthesis problem. It's doubly exponentially complex in the size of the system specification. So if I have 5 specifications, it takes me 2 to the 5th, that's 32. So 2 to the 32 nanoseconds to solve it. And if I double the number of specifications, it takes me 2 to the 2 to the 10th. That's 2 to the 1,000. That's the life of the universe in nanoseconds, right? So it's like the worst possible scaling. Right? So great problem to solve, except it's unsolvable, right? Intractable, right? Can't do it for general specifications. But kind of a neat thing happened, which it turns out there's a subset of controllers that change a little bit what goes on. Basically what we assume is that we can measure what the environment's going to do and react to it, and the environment is not allowed to change its mind. It's like a Stackelberg game if you do game theory types of things, right? But it's essentially breaking the symmetry. It's not a complete game theoretic thing. I see what the environment's going to do. The environment commits to an action. I see what that action is going to be. I can respond to that. And if you do that, then, and that's not too bad, because you can say, well, that's not fair, right? Why should you get to see when the environment's going to? But you know, I'm running in this iteration, right? So I can say, well, you know, I see that the person's starting to turn. As long as for the next 100th of a second, I, you know, sort of assume they're starting to turn. If they stop turning, I'll know that 100th of a second later, I'll replan. So if you kind of go into this receding horizon framework, right, you can kind of deal with this. So if you assume that, then you can kind of unwrap this execution, right? You say, look, the environment chooses an action. I know what the action is. Then the controller chooses its action. We implement the action of the controller and the environment on the process, and we get a new state. And then the environment gets to see that state. It gets to choose an action. We go through this over and over again. And now you can imagine if we can do that, then I can kind of reason about, well, what action do I have to take, not only to make sure that I keep the system safe right now, but that I eventually hit my progress conditions and other things. So turns out for a certain class of specifications, and it's this class of specifications, it's the complexity of the synthesis problem is cubic in the number of states. Doubly exponential versus cubic, right? It just became a linear program, right? I mean, all of a sudden, right? It's like, whoa. All right, so a couple of things. This is the class of specification. It says that I have to have a safety condition on the environment and a progress condition on the environment. So the environment I have to tell you, here are things it cannot do. And here are things it will always eventually do, right? So it'll eventually get out of the way, or it'll eventually, right, do something. And I want that to imply that I will always be safe and I will always make some progress, right? I'll always eventually make it through the intersection. I'll always eventually recharge, right? You know, but I have to always the environment has to always eventually put power at the recharging station, right? Something like that. Or always eventually have a bike rack that I can get into, right? Something like that. So you get this environmental assumption implying a system guarantee, and it turns out that for this, if you can represent, okay, so here's where I'm lying. So it turns out that representing this specification, you can represent it using a finite state automaton called a Buki automaton. And the mapping from an arbitrary specification, even of this form, to a Buki automaton could be exponential number of states in the size of the specification. But typically not. Typically they're pretty small. So cubic's still pretty good, because usually we get specs that can be represented as relatively small numbers of states, and then we can solve these problems. Okay, so this is called GR1, general reactivity. It is an assumed guarantee style specification, right? Like my contracts, right? Under the assumption the environment does this, the system will guarantee this. So we can also use this to synthesize things between the layers, right? So in other words, the environment might be the layer above me, or the environment might be the other players in the game, right? So it fits in that kind of a framework. Okay, so just to kind of show you a little bit about why, you know, it makes sense that this might be solvable, I'm going to give you a really simple game, and this is a game that Punwelli did, one of the pioneers in this field, and it's called the runner-blocker game. And the idea is the following. We've got a runner, R. The runner can be in any one of 4 states, here, 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 or here. The runner's goal is to get to this state here. There's a blocker. The blocker can be in any one of 3 states, the ones that are labeled red, in the middle, at the top, or the bottom. The blocker wins if the blocker is in the same state as the runner. The runner wins if it gets to the green state G. So the goal is eventually get to G, right, and never be in the same state as the blocker. Right? So you can write that down as a temporal logic specification. So how do we solve this problem? Obviously a very simple one, and you can probably see what the solution is going to be. So the first thing we do, not the way you would really do it, but for this example, is we enumerate all of the possible system states. So here's the state we started in, right? Here's the winning state down at the bottom, right, where I'm on the right-hand side, and every other possible combination. Some of these are losing states, right? So first thing, I can write transitions between all of these, right? So here's how I get from all of these states to all of these other states by either the red ones are the environment, the blocker moves, the blue ones are I move. And some of these are winning states and some of them are losing states. So what do I want to do? Well, I want to get to this state. Suppose I assume I start in that state, then I win. Right? Now I can ask the question, well, what are the set of states from which, if the environment chooses any action, I can choose a subsequent action that will get me into the winning state? Okay. Well, that's this set of states.
Question.
Yeah.
In each time step, do they move simultaneously or?
So remember I broke it, right? So essentially what happens is only one moves at a time, and I know, right, ahead of time what the blocker is going to do. So in other words, I'm the runner. You have to decide. You're going to move left. Great. I know you're going to move left. I now get to decide. You can't change your mind. You have to move left. So each, sort of the red arrows are there. They don't happen at the same time. One happens, then the other happens. Now, effectively, I could think of these two happening at the same time. It wouldn't change much, but think of it. So if I start in either one of these states, then of course it's pretty obvious, right? So here, I'm up here. The blocker's down here, right? The blocker can only do one thing. It can move up here. That's fine. I'm going to move here. I'm going to win. Right? Now, of course, at the next layer, so now I've got a new set. This is also a set of winning states. Iterate. So I'll use this as the set of winning states. What are the set of states from which, right, if the blocker takes any action, then I can find a counteraction such that? Well, that's, of course, this top state. That's the only one I add. And the idea here is that if the blocker moves up, right, then what I'm going to do is move down. Because now I know I can win. What I'm not going to do is move the other way, because then I would lose. So what you do is you run a fixed point algorithm. You say, here's the set of winning states that I know. Now expand that to the set of states from which I can choose an action, so let's say win. Now expand that. Keep doing that until you run out of states. Now ask the question, is my initial set in that winning set? My initial conditions, my initial set of states. If so, then there's a strategy by which a reactive controller can always win the game. And what do, right? Well, if I start in any set, like R2, I need to choose the action that gets me into R1. And once I'm in R1, I need to choose the action that gets me in R0. That's my strategy. There may be more than one, right? So I can optimize over that or do other things. So that's the way you can solve this problem. And it turns out that's a cubic complexity problem in the number of states, right? There are good algorithms for solving that problem. Okay, so that's sort of what that looks like. Okay, so I think I want to stop there because we're basically out of time. And so let me just sort of summarize a little bit, right? So what I've tried to tell you a little bit about was a couple of ideas coming from control theory. And so one is that feedback is a tool to provide robustness to uncertainty. I don't know which way the blocker is going to move, so I have to measure what happens, right? I don't know how many people are in the room. I don't know what the road conditions are like. Whatever the uncertainty is, feedback is a tool for doing that. Uncertainty can be noise, disturbances, unmodeled dynamics. Feedback also helps us design the dynamics of the system. That's important in layering because I want to know that the dynamics of the system at that layer are something simple, right, from the point of view of the upper layer. So I want to design them, right, to be something simple so that I can reason about it. And when you combine these together, that's what allows us to use feedback often to get modularity and hierarchy in these systems. Control theory is something that, the tools were originally designed for these lower level control systems, PID controllers and other things. But increasingly, they're being applied to these network systems with hybrid dynamics, mixtures of discrete and continuous dynamics, for example, along the lines of what I showed you. And there are a lot of interesting challenges left to go. I've given you a blazingly fast introduction to all of this, of course. But I will plug a book that talks about this. So with the exception of the very last part, every figure you saw came from this book. Okay? This book is free, so it's a free download. So you're welcome to go to fbsbook.org, feedbacksystemsbook.org, and you can get a free download of this book. If you want the version that doesn't have a lot of bugs and errors, etc., go to the first edition. There's a second edition. That's what's on the homepage. That's the one we're working on, so it's the latest one that's there. We're writing up some of the stuff I talked about at the end, right, for the newest edition of the book, but we haven't gotten there yet. So, but you're welcome to take a look at that, and probably a better resource than that is me. And remember, I'm here, and I'm happy to talk to you, and I'm here, Tuesdays through Thursdays most weeks, and so I'd be happy to, hey, this idea seems like this. Can we talk more? Absolutely. So, with that, I will stop, and thank you for your time and attention.
So we have time for a few questions.
Yeah.
So, for this last part of the synthesis,
Synthesis. Yeah.
synthesis of the, so usually what I've seen always is that you have a guarantee for the safety or something, so it's a certain condition.
Right.
But for example, I don't know the blocker, if it's go 50-50 up or down, so is it like some sort of generalization to do now? I'm caring about the expectation or something, the best I can do.
Yeah, so you can do a couple of things. So in the kind of version I gave you, I'm going to give you a bound on the blocker's behavior, right? It can only move one square at a time or one motion at a time, right? Things like that. I'm going to give that to you as a finite state machine or a temporal logic formula or whatever. And then I'm going to solve the worst case problem, right? No matter what the blocker does. It can be non-deterministic. It could do any one of 5 things. I'm going to reason about every possible case. People have also done things where you say, but what if it's actually like a Markov chain, right? And so with some probability it's going to do this and this, right? And then I can say, first I could still say worst case, but I could also say, well, I'd like to win most of the games. Yes, that can be done. And so there are probabilistic versions of all of this, and you can do probabilistic synthesis. It tends to turn into a Markov chain, choose the parameters of a Markov decision process to get some stationary distribution of the underlying Markov chain. But there are efficient algorithms for doing that, and people have layered on top of it these sort of temporal logic formulas, which after all are formulas on paths through the Markov chain, right? So you say, for example, and always eventually in a Markov chain, often will be a cycle. Right, so you're looking for a cycle that goes through some set of states over and over and over again, right? So now you're looking for lasso, like not lasso like the optimization lasso, but lasso like it's got a sort of a finite part and then a cycle at the end, and you're searching over those things for things that satisfy the right probabilities. So yeah, you can do those too. You had something.
You had a question?
It's maybe too vague to be a question, but you have a process that you view as a box with inputs and outputs to be controlled. But there are lots of systems in the world, especially social ones, where that process itself has feedback loops inside it. I think that, like a national economy,
right,
you might very well want to control.
Right.
But the process within the economy is in some sense resisting control. So is there a theoretical basis for dealing with systems of that kind?
Some. So as you already alluded to, part of the problem is that we have to reason about these systems using some model of what the behaviors are, right? And if those models are not accurate, for example, if I say, well, if I invest in this technology, right, then society will, do this, that, or the other, but society says, the hell I'm going to do that because I don't want to. That's not in my model. Now I can go way wrong, right? Because of course I reasoned assuming one thing and it turned out to be something different. And that's, I think, a big, where you see control systems being applied, I think, quite successfully, are in systems where you have good underlying physics-based models, for example, right? We're pretty sure what we know of the laws of physics for an airplane are, or a room, or whatever. There may be variables there, like how many people are in the room, et cetera, but I can bound that, right? I can say there's no more than however many seats there are, and there's a certain number of BTUs per person, and so that's an upper bound on the amount of heat load. So those are the situations where it works well. What people are trying to do for situations that you can't model as well is use data-driven models, right? So I'll just do representation. I'll give you an example of one that kind of shows maybe what can be done. So, and also some of the pitfalls. So we were trying to do some problems where we were doing robot path planning through a crowded cafeteria. So the idea is I want to go from here to the salad bar, but there's a bunch of people in the way. Right? And if you solve it as a standard robot path planning problem, you say, well, what I'm going to do is I'm going to predict where everybody's going to be, and I'm not going to move in any way that somebody might run into me. Okay? And if you do that in a crowded cafeteria, you will stand there and never move, right? Because there's always people cutting in front of you. The whole point is when you walk forward, they're going to stop, right? But they're not going to stop until you walk forward, right? Okay, so then what do you do, right? Well, okay, so you can model that because you can take data, right? And watch what people do. And now I can do Bayesian inference, essentially, right? I can say, well, let me, sort of say, if I move forward, what's the probability this person's going to stop? And if that probability is greater than 99%, I will treat that as a useful action, right? So we did that, and indeed we were able to move through the cafeteria, right? And we would do what you would expect, which is you walk in front of somebody, they slow down, you keep going, right? It all sort of works beautifully. Until the people say, oh, that's a robot, right? Huh, I'm going to stand in front of it, right? It's like you're trying to move by it, and then they're like standing in front of you, and they break all, because they didn't do that to other people. It's not in your data set, right? And so, it's exactly the same type of thing, right? All of a sudden, like, people get these funny feelings, right? People in autonomous cars are worried about this, right? Because, you're going to say, oh, it's an autonomous car, just walk, don't worry about what the light says, right? It has to stop, right? Well, yeah, right, but the model that it used to figure out, what to do probably didn't predict you were going to walk right in front of a car going 30 miles an hour, right? They could barely stop, right?
So hitting a few pedestrians is a way to change that.
Yes, right. We'll change the behavior on the other side, right? So, yeah, exactly. Anyway, but you're absolutely right. So these are limited to things where you have some ability. If you want the robustness in the way that control theorists think about it, you need some ability to reason about the bounds on behaviors. And if you break outside of those bounds, all your guarantees go away. Yeah, it's a great question.
Here's a question. This is a question from 30,000 feet. So you're going to have multiple autonomous vehicles on the road, each using their own control system. Is it a good idea or a bad idea to have standards and homogeneity in the control? Or is it dangerous to have different controls being used by different?
So I guess one answer would be that there need to be probably an agreed upon set of contracts, which could just be the rules of the road, right? You will stay in your lane, you will stop, when the light turns red and things like that, that facilitate that interaction, right? And so they may not need to coordinate or make use of information from each other or have a common system as long as they've got a common specification, right? And that specification can allow me to implement things differently than you do, just like people drive differently than others. That could be okay. Of course, if everybody implements things in exactly the same way, that could lead to a lot better uniformity, right? And maybe a lot higher traffic flow, et cetera. My own personal feeling is that the difficulty with that is that those sorts of things probably make sense when 100% of the cars are autonomous, but we're not there. And I can't tell you how to drive, right? I mean, you're going to drive like you're going to drive. And so we probably have to solve the problem of other agents that you're interacting with not following the same even rules that you're following, let alone implementing it the same way. So we probably have to solve the problem. But yeah, if you can, so I'll give you a different example. People who know Amazon bought Kiva Systems. Kiva Systems does these warehousing robots, right? They all behave by exactly the same rules, right? So you know exactly what's going on. You can replace any one with any other one, right? You can reason about them because you know exactly what they're going to do, and they all implement the same control algorithms. That's a good thing, right? But they're in a very controlled environment. So it probably would make the problem easier because everything would be kind of symmetric. But I don't know that we can. I don't know how to get from here to there, right? Except in these very controlled environments, like a warehouse where you're going to control everything in there.
I mean, there is some security considerations as well.
Yeah, so the other one you would worry about, and just say the aircraft control industry worries about this a lot. Not so much because of adversarial stuff, but one of the things they worried about a lot was, you typically in an aircraft, depending on how safety critical it is, you have 2 or 3 processors doing your flight controls. And they'll vote, they use a Byzantine consensus algorithm typically to make sure that, right, sort of if a controller fails, right, that the right thing happens. But the other thing they worry about is common mode failure, right? So there's a bug and it's the same algorithm running on each one, and so the same bug, right, they all interpret the signal differently. So the way they handle that often these days, I mean, now they're getting a little bit less paranoid about it, but in the old days, they would have different teams design each controller in different programming languages implemented on different microprocessors, right? To make sure, right, that if the Intel floating point failure or whatever was in one of them, right, it wasn't going to be in the other 2, right? And so that's what they would do. And that, of course, could also give you something for adversarial attack, right? There's the attack vector is, I'm going to hit, some number of your processors and not all of them. So there's another one where you might worry about if everything did it the same way and a virus spread through, right, your entire traffic system will fall apart. Yeah, absolutely.
So how do we deal with the time sink problem in distributed and dynamic systems where all those things are actually moving? So they have to incorporate the changes in their internal clocks into their internal clocks at a given moment.
Yeah, so a starting point for that is so computer scientists have also thought about this, and you can think about banking transaction systems, distributed things like Bitcoin and other things. And so there are consensus algorithms by which we can all guarantee that we reason about things in the same order. Right? So you use logical clocks and vector clocks for people who are computer scientists. The problem with those things are that they are not fast. So they're not designed to be implemented in real time particularly. And so you can do things where you say, so now I think the way people would deal with it is they say, well, we allow some amount of clock skew, but we control very carefully the clock skew, and then we have to prove, right, that if I've got 10 processors and they could each have a millisecond clock skew in any direction, that this algorithm will always do the right thing independent of the interleaving with all of those. So that's now a verification problem, right, where you worry about doing verification over interleaving executions. And some of that can be solved via verification, but usually in a, I guess I would, and I'm not a super expert in this, but usually in a very specific case. If I tell you there are 10 processors and here's the amount of error, et cetera, I can do it. If I tell you, well, I don't know how many cars are going to be on the road, right, and they're all going to have slightly different clocks, and they're all going to see the red light turn at a slightly different time, right, and I need to reason about that. Generally, I don't know how to do that problem yet. So there's starting points, but it's not solved.
Isn't there some fundamental trade-off between how much do you spend on ensuring the clock sync and essentially establishing consensus, and how well does your environment decides its action doesn't change its mind approximation work in the system?
Yeah, so if you can do something where you can just make it, for example, kind of time shift invariant, right? That's the ideal thing, right? It doesn't actually matter, right, that the clocks are off. Right? And so then I don't have to spend any time doing consensus, right? I think most of the time you can't do that. And so now what you said is a great trade-off, right? So like how much, so somebody asked me this question during the breaks, time delay is one of the things that works very badly with feedback control systems, right? Because if I tell you to do something and there's a long delay between when you do it and there's another long delay between when what you did and what I see actually happens, right? I can get out of sync, right? And so you see this like in your shower sometimes, right? You sort of turn the shower to hotter, it doesn't get hotter, so you turn it up more, right? And then it gets too hot, right? Because there was a delay, right? So then you turn it way down, right? And it takes you a while to settle in, right? So those delays are a problem. Consensus algorithms could have delays, and so that would be a trade-off, right? I want to do it fast, but maybe I can't do it that well. It's a good question. I don't know. I'd love to talk more about it. Maybe there's a nice mathematical formulation in there that could be put together. Yeah.
So regarding the last part of your talk, so you said that there are a class of systems for which the complexity is cubic and the state space size or something like that, right?
Yep.
But from what you described about how one would actually go about, solving, right? So it seems like either one would be solving a fixed point problem, or one would be enumerating. So I don't understand. So both of them seem, they're intractable problems. They have exponential complexity. So
yeah, so the way you solve it is that you represent your formulas as BDDs, binary decision diagrams, and then you do reasoning at the level of BDDs. And so I give you a BDD that describes the winning set, and then I compute out a BDD that describes the next bigger one. And it turns out you can, for GR1 specifications, you can encode those efficiently. And that's what they're able to show is essentially a kind of cubic calculation. And I think it's cubic in the basic algorithm, and then implementing in BDDs allows you to solve very large problems. So we'll typically solve things that might have 10 to the 9th states or something like that, right? So billions of discrete states between the specification and the control system, and the algorithms for doing it are not particularly complicated. Maybe a dozen lines of Python code, sitting on top of a BDD library that's implementing everything. So, and I'm happy to, there's a program called Omega that does this in Python, for example. It solves those problems. And there's a BDD library that it sits on top of called DD. So, yeah. But it works.
there's a question.
Yeah.
It's a very practical problem, so the answer could be just go read Wired magazine or the Wired trade backs. But over the last 10 years, we've gone, with respect to UAVs, N-copters in particular, from academic somersaults to stuff that's on the shelf at Fry's.
Right.
How would you care? Were there any advances in the control aspect of that made that possible, or is it just that batteries got low enough so that there's enough power to give a couple of minutes of...
No, I mean, a lot of technologies all at once, of course, right? And control was one of those. So, one of the things that makes, quad rotors work is that, more or less you say hover and it just hovers and holds, right? I mean, they're really good controllers, right? So why does that work? Well, that works because they have pretty accurate gyros and accelerometers, right? And so that's a technology that your cell phone is driving, right? Because they're getting better and better and better, right? Like the shake alert stuff, et cetera. they have lots of computation. So what you want to do is you want to compute very quickly, right? Because you want to, if you want it to be rock solid, you want, if it's off by, a microradian, right, that you correct a little bit, right? That means that, as this thing's moving around, you need to be computing fast enough to see that. That's another, the reason the control systems work so well is because we can put, pretty fast computation on those with really good sensors that are very accurate and have low noise, and all of that just comes together. And the motors can react fast enough, right? So that, these little tiny motors that people have been making now, they've, optimized them and other things. So I wrote a robotics book way back, and one of my co-authors was Zhe-Sheng Li. Zhe-Sheng Li's master's student is Frank Wang. Frank Wang is the CEO of DJI, right? And so if you go talk to them, right, this is what they say. Basically, they'll tell you what's driving DJI is they use cell phone components for almost everything except the motors. Right? And they wind their own motors, right? They make their own motors, so they can get the performance that they need. But all of the computing, all of the communications, all of the gyros and other things, all of the cameras, et cetera, all of that is going forward because of cell phone technology, and that's just making it cheaper, higher performance, right? Letting you put more things on there. So the motors are now good enough, right, for these small things. It helps to get them smaller because big motors are hard to get to move fast, right? So that's, I think, a lot of what's driving it.
Possible lessons for autonomous land vehicles?
Maybe. I think on the land vehicle side, honestly, the hardest part of that problem is driving in environments with humans, because you have to reason about what the humans are going to do. So, if you just want to drive and, if you look at these autonomous cars driving, they're very smooth, they're very fast reacting, they're as good probably as a human in terms of just maneuverability and other things. The challenge that they have is they come up to some weird stoplight situation they've never seen before, right? Because there's a flashing light in some weird spot that gets them confused, et cetera, right? Or there's a person who's looking at their cell phone and walking in front or something like that. I mean, that's where I think the hard parts of the problem are. The control, that's a control problem, right? It's just a higher level, right? The lower level control parts of the problem, where you would say the pace of technology, et cetera. The one sensor one that's there is we don't yet have truly cheap ways of detecting within, say, 100 meters of a vehicle or 50 meters of a vehicle what's going on at the right resolution. Right now, everybody's using like these Velodyne laser rangefinder units. They're $100,000. It's more than the cost of most people's cars, right? And so that's a problem. But everybody is sort of saying, yeah, but we believe that'll be solved. People are going to come out with solid state lidars and, right, sort of solve that problem. So we're going to buy those things for our test vehicles, right? Spend a bunch of money, and then when that solution comes along, maybe from cell phone technology, I don't know, right? The iPhone 10, right, has this, face scanner thing, right? That's some sort of a proximity sensor in some sense. I don't know, maybe.
Okay, I guess let's thank the
Great.
speaker once again.
Thank you very much.
And we'll meet next day, we'll meet tomorrow at